All right, so welcome to the second half of the Schubert seminar with Yuxiang Liu telling us about rigidity of Schubert varieties.
Okay, thank you. Next, I'm going to talk about the case of partial flux varieties. Let our X to be the variety that parameterizes our case that partial flux whose elements are elements in the Grassmannians. And therefore, we have natural projections from partial flux varieties to Grassmannians, which are obtained by just ignoring all the other components. The Schubert varieties can be defined with respect to a reference flux as well as a double index. The lower index A is same as the Grassmannian case. We use a straight increasing sequence to indicate the dimension of the flux elements. So FAI is a subspace of dimension AI. And for the upper index alpha, we use it to indicate the component that a subindex. Now, given such a reference flux and a double index, the corresponding Schubert variety consists of the partial flux whose components meet FAI in the correct dimension. And it is easy to check that the Schubert varieties are taken to Schubert varieties in Grassmannians under the natural projection. Then we can define the essential subindices, rigid, multi-rigid subindices, just in the same way as Grassmannians. A subindex is called essential if it is essential with respect to some push-forward indices. It is equivalent to say either this condition is true, either A is not AI plus 1 minus 1, or the upper index is increasing, alpha I minus alpha less than alpha I plus 1. And an essential subindex is called rigid. If for every representative there exists, we can find a subspace of dimension AI that meets all the components of all partial flux in Y in the correct dimension. And we can define the multi-rigid subindices in the same way. And this theorem allows us to deduce the rigidity or multi-rigidity for partial flux varieties from the result of Grassmannians. An essential subindex is rigid or multi-rigid if it is rigid or multi-rigid with respect to some push-forward classes. And here is an example. We consider a subvariety Y whose class is given by a multiple of this class. The lower indices are 2, 3, 6. Upper indices are 2, 1, 2. So this means the upper index of 3 is 1. So 3 will occur in the first component. Its class, it is taken to sigma 3 under the first projection. And it is taken to the Schubert class sigma 235, 236 under the second projection. Both classes are in Grassmannians, so we can apply our result from Grassmannians. We get the subindex 3 is multi-rigid with respect to the second class, which means we can find a subspace F of dimension 3 that meets the second component of 4 points in Y in dimension at least 2. Then we claim that this F3 also meets the first component of 4 points in Y in the correct dimension. in dimension at least 1, so that the subindex 3 is multi-rigid with respect to the class for partial flower varieties. To prove it, we take a general point in the image of Y under the first projection. And then we take its pre-image in the partial flower varieties, then we push it forward to the second component. The class of Z only depends on the class of Y if we allow a difference on the coefficients. The class of Z is given by some multiple of the class sigma 136. Then we can consider the variety phi, which is the variety swept out by the k-planes parameterized by Z. We can compute its dimension. The dimension equals the largest subindex minus 1. So the dimension equals 5. Now suppose for contradiction that lambda 1 has 0 intersection with F3. Then that would imply the intersection of lambda 2 with the span of lambda 1 and F3 has dimension at least 3. It is because for every lambda 2 in Z, by our construction, lambda 2 must contains our lambda 1, and therefore the intersection of lambda 2 and lambda 1 has dimension 1. And since 3 is multi-rigid in the second component, that means that intersection of lambda 2 and F3 has dimension at least 2. So this together gives the dimension of intersection of lambda 2 and gamma is at least 3. In fact, this lambda 2, our lambda 2 has dimension 3. It is a 3 prime. So it is equivalent to say gamma contains all lambda 2 in Z. That means this gamma coincides with our phi. But it's a contradiction, since the dimension of phi is determined by the class of Z. The dimension equals 5. However, the dimension of gamma, which is a span of lambda 1 F3, dimension is 4, or projective dimension is 3. So we get a contradiction. We conclude that the subindex 3 is multi-rigid with respect to the original class. And here's a remark. For the rigidity, this theorem is sharp. An essential subindex is rigid if and only if it is rigid with respect to some push-forward classes. However, for the multi-rigidity, this condition is only sufficient but not necessary. It can be seen from this example. We consider an index. Consider this index. Under the first projection, it is taken to AI plus 3. It's just a subsequence that consists of the elements whose upper indices are 1. So we have AI, we have AI plus 3, but we don't have AI minus 1. We don't have AI plus 2. Under the second projection, we have everything. We have AI minus 1, we have AI plus 2, AI plus 3, and so on and so forth. Then we can apply our multi-rigidity result from Grassmannians to get the subindex AI is not multi-rigid in both components. Under the first projection, AI is not multi-rigid since we don't have AI minus 1. And under the second projection, AI is not multi-rigid since the difference on the right side is 2. We have AI plus 2 here. Nevertheless, we claim that the subindex AI is multi-rigid with respect to the original class for partial Floer varieties. For proof, we first consider its image under the first projection. Since we have AI and AI plus 3, we can find a projective variety phi of dimension AI minus 1 that meets all the points in the correct dimension, or the points in a representative in the correct dimension. Then one can show that this phi is also good for the second component. Phi would meet the second component of all points of all partial flux of a representative in the correct dimension. And on the second projection, we have AI and AI minus 1. This condition ensures phi is a linear space. And thus AI is multi-rigid with respect to the original class. In fact, this condition, together with the theorem, gives a sharp description of the multi-rigid subindices for partial Floer varieties. Now we have a characterization of rigid and multi-rigid subindices. We want to use it to classify the rigid and multi-rigid Schubert classes for partial Floer varieties. There's one difference between the Grassmannians and partial Floer varieties is that a Schubert class for partial Floer varieties may not be rigid or multi-rigid, even if all essential subindices are rigid or multi-rigid. It can be seen from this example. We consider the Schubert class. In Schubert class, the lower indices are 1, 3, 4. Upper indices are 2 and 2. In the partial Floer variety of 4 point in a 3-plane. Under the first projection, it is taken to sigma 3. And under the second projection, it is taken to the Schubert class sigma 1, 3, 4. All the subindices are rigid in this case. The index 3 is rigid under the first projection, and number 1, number 4 are rigid under the second projection. However, we claim that this Schubert class is not rigid for the partial Floer varieties. We can construct a counterexample. We pick a 3-plane F, F3. Then we take a point F1, which is not contained in F3. Then we consider the locals of all pairs. We pick lambda 2 to be a 3-plane that contains F1. And we pick lambda 1 to be a point in the intersection of lambda 2 and F3. Under the first projection, we can see that lambda 1 could be any point in F3, so the class is sigma 3. Under the second projection, we can say lambda 2 could be any 3-plane that contains this fixed point F1. So the class is given by sigma 1, 3, 4. So the class of Y is good, but we claim that this Y is not a Schubert variety. It is because F1 is not contained in F3. So Y cannot be defined by a partial flux. So it tells us that we need to impose some extra conditions so that the subspaces corresponding to essential subindices form a partial flux. And such conditions are illustrated by this lemma. We consider a Schubert class for Grassmannians, and we take a representative. Assume there are two subspaces that meets every point in X in the correct dimension. Then if the larger one is essential, we have the inclusion. These two subspaces form a partial flag. And this leads to the following definition. We define a relation between two subindices. We draw an arrow from the smaller one to the larger one, if the larger one is essential in some component. And this relation extends to a straight partial order on the set of essential subindices by transversity. And this leads to the following corollary. A Schubert class is rigid or multi-rigid if and only if our essential subindices are rigid or multi-rigid, and the set of our essential subindices is strictly or totally ordered under the relation that we just defined. So this gives a full classification of rigid and multi-rigid Schubert classes for partial flag varieties. The last case is the orthogonal Grassmannians. Here we take our X to be the variety that parameterizes our isotropic subspaces of dimension K. The isotropic subspaces are defined with respect to a symmetric bilinear form Q. For simplicity, we will assume our N is odd, so it is of type B. When N is even, almost the argument would work, except we need to make some adjustment above for the maximal isotropic subspaces. The Schubert varieties, again defined by a flag of isotropic subspaces. So each element of this partial flag is an isotropic subspace. And we will use a double index A and B. The left index is a straightly increasing sequence, which is same as Grassmannians. We use AI to indicate the dimension of AI. So FAI is an isotropic subspace of dimension AI. The right index, we use it to indicate the dimension of the singularities, the dimension of the singularities of the quadrats. Now, given a reference flag F and a double index, the corresponding Schubert variety is defined to be the locals of all isotropic subspaces that meets FAI in dimension at least I and meets the orthogonal complement of FBJ in dimension at least K minus J plus 1. It turns out that we need to impose some conditions on the defined sequence so that this locus, this sigma, is irreducible. The first two conditions corresponding to the fact that the maximal dimension of isotropic subspaces containing a vector space of dimension n is half n. And the third condition says AI minus BJ is not 1 for any AI and any BJ. And here is an example. If the condition 3 fails, then the locals and the sigma will split into two sublocals, so the sigma is not irreducible. This example, consider this example F2 containing F1 probe. Here we also assume F1 is containing F2. Then it will split into two subsequences, F1 containing F1 probe and F2 containing F2 probe. Now for every 2-prime lambda that meet F2 in dimension 1 and containing F1 probe, there are two possibilities. If lambda contains F1, then lambda must be contained in the locals defined by this sequence F1 in F1 probe. If lambda does not contain F1, then lambda must meet F2 in a point different from F1 that we denote by F1 prime. And therefore lambda is contained in the orthogonal complements of these 2 points, and thus it's contained in the orthogonal complement of F2. So this means lambda is contained in the locals sequence F2 in F2 probe. A remark is that for the maximal orthogonal Grassmannians, when n equals 2k or 2k plus 1, the sequence B is uniquely determined by the sequence A and the relation and this third condition. And vice versa, the sequence A is uniquely determined by the sequence B and this relation. I will talk about 2 approaches that can be used to prove some rigidity result for orthogonal Grassmannians. The first approach is consider the inclusion, the natural inclusion of the orthogonal Grassmannians into the Grassmannians. We can compute the push-forward cost of a Schubert cost in orthogonal Grassmannians, and then we can apply our rigidity result from Grassmannian cases. For example, if we consider a Schubert cost 2, 3, 0 for the orthogonal Grassmannian of J3n. To compute this push-forward cost, we specialize the subquadrats to subquadrats with small singularities, which correspond to we increase the values in the right sequence. In this case, we replace 0 by 1. And now for this Schubert cost, the condition 3 fails, and thus it will split into 2 sequences. It will split to sigma 1, 3, 1, as well as a sigma 2, 3, 3. Then we can increase the singularities again and repeat this process. When we will stop when the number in the right sequence becomes half of the dimension minus 1. So for example, when we reach 2n minus 6, the Schubert cost, we have the Schubert cost 2, 3, and minus 4. The orthogonal complement of an isotropic subspace of dimension n minus 4 would intersect the quadratic hypersurface in a union of 2 maximal isotropic subspaces of dimension n minus 3. And if we consider it in Grassmannians, that gives us 2 copies of sigma 2, 3, minus 3. And finally, we get the push-forward cost is given by the sum of these 3 classes, and the coefficients are 2. It is a cost for Grassmannians, and we can apply our result in Grassmannians to conclude that the subindex 3 is multi-rigid. there exists a subspace of dimension 3 that meets every point in dimension at least 2. Meets every k-prime, meets every 3' in dimension at least 2. The second approach is what I call correspondence. We can make use of the orthogonal partial Floch varieties that parameterizes all k-step partial flux whose elements are isotropic subspaces. Then we can argue that then we can deduce the rigidity or multi-rigidity of one component from the other components. For orthogonal partial Floch varieties, the Schubert variety can be defined in the same way. The lower indices is same as the orthogonal Grassmannians, and the difference is we add extra upper indices to indicate the component that a subindex first occur. And again, the Schubert varieties are taken to Schubert varieties in orthogonal Grassmannians under the natural projections. Then use the same idea, similar argument as the partial Floch varieties of type A. One can prove that for representative Y of a multiple of a Schubert class, if a subindex is essential and the corresponding Floch element Fai or Fbj probe intersect the Tth component of all points in Y in the correct dimension, then that would imply these Floch elements also intersect all the other components of all points in Y in the correct dimension. We can use this observation to deduce the rigidity or multi-rigidity for non-maximal Grassmannians from the maximal orthogonal Grassmannians. For example, assume Y is a subvariety of a non-maximal orthogonal Grassmannian, which can, assuming it is irreducible with class, the class is given by a multiple of a Schubert class. Then we can consider the incident correspondence of a point in Y and a maximal isotropic subspace that contains lambda. Here I forgot the relation. We take lambda prime contains lambda here. So it is a subvariety that contained in the orthogonal partial Floch varieties. We can compute the class is class in orthogonal partial Floch varieties, and we can compute its push-forward class. The class of its image under the second projection is given by some multiple of the Schubert class, where the sequence A is same as the sequence A for our variety Y, but our sequence B prime is the maximal admissible sequence associated to the sequence A. It is determined by the sequence A. It is a sequence determined by A and the relation that AI is not Bj minus Bj plus 1. Just recall our third condition here. It is determined by sequence B is uniquely determined by the sequence A and this relation. So this B prime is a maximal, so B prime is a sequence determined by A. And the image of I under the second projection is just a multiple of this Schubert class. Okay. Then by the previous observation, that tells us that if there exists, if AI is rigid or multi-rigid with respect to this Schubert class for the maximals on the Grassmannian, which means we can find an isotropic subspace of dimension AI. That means all the second components in this in I in the correct dimension, that would also intersect the first component of all points, which means it would intersect all the k points in Y in the correct dimension. That implies AI is also rigid or multi-rigid with respect to the class for OJK, which is not maximal. Okay, we stop here. Thank you.
All right. Thank you very much.